Alright, so welcome to week 10 problem solving session. I am Shreya, the TA for this course, and today I'll be discussing few problems which are related to concepts which were discussed during week 10 lectures. Okay, before moving on, any questions from the previous sessions? If you have, you can say. If not, I'm going to start today's session.
Question, ma'am.
Alright, so like always, I'm going to start with the concepts that were discussed during week 10 lectures. So we learned a little more about dummy variables. So previously we had learned how to take care of dummies, or how to code categorical variables into dummy variables when these would be included as a regressor in our model. So we learned something more on that, and also we learned about techniques that we should use when the dependent variable, or in other words the response, or uh, the dependent variable, what happens, how to tackle these situations where the response variable is categorical. So in that cases also we used dummy variables. How we learned a few of the models with which we could do so. Before that, just to brush up, so we learned about some dummy variables, like if we have, let's say, a regressor as gender, so it could be male, female, or others, something like this. So in order to incorporate these, we would use some encodings, like we would use x 0 1, like we could use two dummies in this case, 0 and 1, to get hold of these three regressors in the model. We learned a lot about these things. Also we learned how to uh, categorize or separate a regression equation based on intercept and slope dummies. So if we have an equation, like let's say this is for males and this is for females, if during the lectures it was discussed, let this regression be for wage, then initial wage could differ between male and female, but based on experience it could the increase or increment could remain same, or it could be differential. Like we could have something like this, that the intercept is different but the slope is same, or both the slope coefficient and intercept coefficients, they differ with respect to different categories. So those kind of things were modeled using intercept and slope dummies. We also learned about the dummy variable trap, where uh, we would face problems of multicollinearity, and that would not yield us good and accurate uh, estimates of the regression equation, because of the fact that even though in the presence of multicollinearity there are certain problems, like the standard errors would be more, the estimation will not be accurate, and we would falsely reject hypothesis. Those kind of situations also arise when we have problems of multicollinearity, which can arise due to this dummy variable trap. Also we learned about how to use f-test in order to truly judge that do we need separate regression lines for separate categories of a categorical variable. So for those kind of situations we would use that restricted versus unrestricted framework, and using f-test we would go for testing. We also learned about uh, as I was saying, the dummy dependent variable, when instead the response variable, instead of being continuous as it has been for so long, like in the previous lectures, now what happens if we have the response itself as categorical, let's say a male female thing, or a yes no kind of a thing, or some disease status, diseased or otherwise healthy, something like that. So in those cases where the dummy the dependent variable can be modeled as a dummy variable, it is not fair to use the OLS estimations, because those kind of things do not work there. Because if we have something like we discussed, if there's a 0 1 thing, we would have points scattered near 0 and points scattered near 1. So then the normal OLS regression would not work, because we could have certain predictions which fall outside the range, and it would not be wise to cap those predictions at so if this is the predicted probability and this is x, so it would not be a wise decision to cap it, and to make this thing bounded between 0 and 1. So we would make certain transformations. We could also I mean we could use the probit, or uh, so this one that I'm talking about was modeling the probabilities in a linear fashion. So these has certain disadvantages, like the estimated probabilities could be more than 1, could become less than 0, and it would not be wise to cap those at 0 and 1. So alternatively, we could use the probit or the logit model that would kind of restrict the curve, the that would do some sort of transformation on this linear equation, linear on this linear equation, that would finally have, so that we finally have, like if this is the case of a sigmoid curve which occurs when we do that logit transformation, so some kind of transformation which would bound the predicted probabilities within that 0 1 range. So we discussed two of those probability models. One is the probit model, and the second one is the logit model. And then we learned about how to estimate, like a little bit about the estimation procedure, the method of estimation, which is the maximum likelihood method. We learned a lot about the connection between odds ratio and a logistic regression equation, and also we learned about the goodness of fit test in that logit case, which would be some form of ratio of fitting the full model by fitting ratio of two likelihoods that would be obtained by fitting the full model by dividing by the likelihood that we would obtain when only the intercept term is fit. So with that pretext, I am going to move on to the the problems and uh, their solutions. So as an when as we go about the problem solving sessions, these concepts, I hope they'll get more and more clear to you. Okay, so shall I move on?
Yes, ma'am.
Okay. All right. So this is the first question. So we consider fitting a regression model with a continuous variable x1. Y is also a continuous. If nothing is mentioned and the linear form is given, it is safe to assume that y is also a continuous variable. X1 is also a continuous regressor. So now if you have to incorporate one categorical variable with three categories, then how many number of dummy variables you need to add to the model? So we already have this thing. So if we write the model matrix, so if you remember, we can write the equation as this thing. in a multivariate form. So then the X matrix would be, the first column would correspond to the, would be 1 corresponding to the intercept term beta naught, and the second one would be, let's say if I write x11, x12, x13 dot 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 x1n, that would correspond to the term x1. And if we write the beta vector as beta naught and beta 1, so then x beta would give us this form. Y would be y1, y2. These are like observations. Okay. So then if we write this equation in this form, then we would get whatever is written over here. Like y1 would be beta naught 1 into beta naught plus x11 into beta 1. So this is falling in this scope, plus epsilon would be epsilon 1, epsilon 2, epsilon n, something like this. I hope this multivariate form is clear to you. I have also discussed this previously, but just to brush up, we can, even if we have one regressor, we can write it in this form, and this capital X is my model matrix. So if you remember the OLS estimate, how we got it by X transpose X inverse X transpose Y. This was the multivariate form in which we would get the OLS estimates. Now the problem here is we have to get an inverse of this X matrix, or X transpose X is not square, so we won't be able to do an inverse. We have to do an X transpose X and then take an inverse of that matrix. Now in order to have an inverse of this X transpose X, the criteria is the columns of the X matrix should not be linearly related. Okay, so the general idea is, if we have a categorical variable, let's say with n levels, then we should have n minus 1 dummies excluding the intercept term. So what I mean to say is that if let's say this is my X matrix where we have all 1, okay, let's say I'm taking 6 observations like this. So x11, x12, x13, x14, x15, x16. This corresponds to the variable x1. This corresponds to the beta naught column. Now we have a categorical variable. We have a categorical variable which can take 3 levels, let's say A, B and C. So we have 3 variables, 3 levels of this categorical variable. So we can use 2 dummy variables to model these two. So let's say if we design our dummy variable is, let's say this is my reference group. Okay, so I say D1 is 1 when we have category A, 0 otherwise. D2 is 1 when we have category B, 0 otherwise. Then if we have this thing, let's say the first observation belongs to category A, so then we could write it as 0, 1. Let's say the second observation belongs to category B, then we could write it or designate in terms of 0, 1. Let's say the third one is in category C, so we could, it's not A, it's not B, so 0, 0. Okay, like this we could go on and make the categories. Let's say again we have something like this, 1, 0, 0, 1 and 0, 0. Now this kind of modeling will not put, if we add these two up, if we do d1 plus d2, we would have something like 1 1 0 1 1 0. Okay, so this is not exactly linearly dependent with beta naught. We cannot make any linear transformation of beta naught so that we get this thing. Okay, so then what happens? These columns become linearly independent, and so x prime x inverse, the inversion of x prime x is possible. This will exist, and we would get beta hat OLS values. So the crux of the matter is, if we have a categorical variable with n number of levels, we should use n minus 1 dummies excluding the intercept term. So including intercept, there should not be more than three dummy variables. So here we have three categories, we are using two dummy variables. Now somebody might ask, what would happen if we used three dummy variables? Let's say we have three categories. Okay, so we'll use three dummy variables. This is 1 if A, 0 otherwise. D2 is 1 if B, 0 otherwise. And D3 is 1 if C and 0 otherwise. So then if we write the X matrix, let's say this is x1, that column. Okay, so the first one was A, B, C, again A, B, C. Okay, so D1, D2, D3. For A, here we would have 1, 0, 0. This would be this, C would be this, again A would be this, B would be this, C would be this. Now we note that if we do like the first column of X matrix is equal to sum of D1, D2 and D3. So then what is happening? This column is exactly linear, then this becomes exactly linearly related, because D1 plus D2 plus D3 would give us this 0th column. So then if there is this exact linear relation, then x prime x inverse is not possible. The unique x prime x inverse is not possible, because the rank of x will be less than p, 1 2 3 4 5. Okay, so that is why for n number of categories, we should have n minus 1 number of dummies, so as to avoid this rank problem, so that x prime x inverse exists, there is no multicollinearity, and we can go ahead with the OLS estimation of the data. Is it clear why we should not have three categories and we should only have two categories?
Yes, ma'am.
Okay, then I'm going to move on to the next one. All right. So consider this model y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Let us consider a categorical variable z with two categories A and B. Will it be possible to get least square estimates if you consider this model y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus alpha 1 z1 plus alpha 2 z2 plus epsilon, where the variables z1 and z2 are like this? Okay, so what will we do? We will draw the X matrix. So here we would have how many columns? they are saying 1, 2, 3, 4, 5, 5 columns. So this would be corresponding to beta naught, this would be beta 1, this would be beta 2, this would be with respect to alpha 1, and this would be respect to alpha 2, let's say. So here we have beta naught is the intercept term. It will be present all throughout 1, 2, 3, 4, 5. Let us consider 6 observations just for the general purpose. So this will be x11, this is x12, x13, x14, x15, x16. This would be something like x21, x22, x23, x24, x25, x26. Okay, so z1 is a. So let us consider that we have 4 A's and 2 B's. Okay, out of these 6 individuals, 4 are in A category, 2 are in B category. So alpha 1 would be 1 wherever we have A's. So let's say the first one, third one, fifth and sixth one are A's, and the other twos are B. Okay, so this observation belongs to a candidate in category A. This one belongs to a candidate in category B. So if we have to code it, then here wherever it say, we would have 1 0, 1 0, 1 0, and here we would have 0 1. Here again, if we just sum these two columns up, alpha 1 corresponding to alpha 2, like I shouldn't write alpha 1 plus alpha 2. Let's say this is C1, C2, C3, C4 and C5. So if we do C4 plus C5, we would get C1. Exactly linearly related. So then rank of x will be less than p, which is 5, and x prime x inverse not possible. So will it be possible to get LSE estimates? The answer is no, because beta LSE or OLS is given by x prime x inverse x prime y. Is it okay? Any doubts? Okay. So I'll move on to the next one. So here we have been given two groups, data corresponding to x and y data corresponding to two groups A and B, and we have been asked to use one dummy variable in order to distinguish these two groups. And to fit a model such as this, y equal to beta naught plus beta 1x plus alpha naught z plus alpha 1 xz plus epsilon. So what will be the LSEs of beta 1 and alpha 1 approximately? So what should we write? So this is my model. So now my y would be, I have to combine. So this will be 51, 8, 68, 25. So I am writing the A group at first, and then I am going to write the B group. Similarly, we should write our X matrix also. Okay. So this one, then we would have 49, 42, 50, 36. Our x would be, so before even that, let us write our beta, the coefficient vector. So this would be beta naught, this one, then beta 1, then we would have alpha naught, then we would have alpha 1. Okay. So the X matrix would be beta 1. For beta 1 we would have coefficients like this, 1, 2, 3, 4, 5, 6, 7, 8. All will be 1. Sorry, beta naught all will be 1. For beta 1 we would have x's. So first I have written x, the A group first. So I am going to write the x for A group at first. 18, 10, 22, 12. And then I am going to write the B group, 19, 17, 18, 16. So this is done. Okay. Then I would have the column for alpha naught. So then we have to code Z. So here Z will be 1 for set B and Z will be 0 for set A. So I have written A at first. So we would have 0, 0, 0, 0, 1, 1, 1, 1. Okay. And the next column will be corresponding to alpha 1. What is the coefficient of alpha 1? This is xz. So for the first categories, z is 0. So here we would have 0, 0, 0, 0. For the second category, for set B, z is 1. So we will multiply 1 with the x's of B category and then that we are going to place here. So for set B, x into z, z is 1. So here we would write 19, 17, 18, 16. Okay. Now we see that we have two categories, set A and set B, and we are using one dummy variable along with the intercept. So there is no problem of multicollinearity in the data. So then we can go ahead and compute this thing. Sorry. Yes. So we can get beta hat as x prime x inverse x prime y, where my x's and y's are this thing. So the formulation is clear to you, hopefully. This is only what matters. Then we just have to algebraically derive x prime x inverse x prime y. So after, if you do this with those matrix, we would get beta, the estimates of betas. I've already done it. So it would be something like this: minus 36.604, 4.813, minus 1.396, minus 0.113. Okay. So using these x's and these y's, we would get a beta hat such as this. Now we have been asked to find the least squares estimates of beta 1 and alpha 1. So then if we compare, our beta was like this: beta naught, beta 1, alpha naught, alpha 1. So then beta 1 hat will be 4.813, this one, and alpha 1 hat will be minus 0.113. Is it okay?
Okay, ma'am.
Okay. So now we have fit this model. Now what does this imply in terms of these things? So if we have a model like this, let's say the model was beta naught plus beta 1x plus alpha naught z plus alpha 1 xz plus epsilon. So for category A, the z's would be 0. So our regression would be beta naught plus beta 1x. For category B, the z's would be 1. So our regression would be beta naught plus beta 1x plus alpha naught plus alpha 1x plus epsilon. So we can write it as plus beta 1 plus alpha 1, something like this. Okay, so we would have, if we plug in the intercept values here, we can see that the intercept term, let's say this is for category A, this will be for category B. Okay, so this intercept is also different. This one is alpha naught plus beta 1 and the total thing is alpha naught, sorry beta naught. Okay, this point is beta naught and the slope coefficients also differ for the two categories. Okay, now we want to find out something. We want to test this hypothesis. So if we plug in beta naught and beta 1 and alpha 1 values, if you see like this, then we want to find out whether this kind of segregation is at all necessary, or will a single line be able to fit the data, or in other words we want to check for how significant these alpha naught and alpha 1 parameters are, because those are only adding to the existing reference category and changing the regression line for the other category. Okay, so if we move to the next question, the question is, we will consider the data in the previous problem and we have to see if a single straight line model will fit all data. Then if that is the case, then what should be the null and alternate hypothesis and what should be our decision. So as I was saying, we have two models. For category A, we have y equal to beta naught plus beta 1x. For category B, we have y equal to beta naught plus alpha naught plus beta 1 plus alpha 1x. Okay, this is category A. Let's say this one is category B. Okay, so the hypothesis is, when will this a same line, when will like a single line such as this, let's say a single line such as this is fitting all sorts of data. So in that case, or let's say two categories are not required, only one is sufficient. So the change is being caused by these two terms. If both the terms are set to 0, then we don't need to fit separate regressions. For category A also we would have this equation, for category B also we would have this equation. So the H naught, the model that we want to test is alpha naught equal to alpha naught, alpha 1 equal to 0 versus H1 is not H naught. Either is not equal to 0. If both are 0, then there is no difference in regression line between these two categories. So in that case, a single straight line model will fit all data. Now we have our hypothesis designed. Now we have to test the hypothesis. So in order to test, what are we going to use? We are going to use the F test. So the test statistics will be sum of squares due to errors from the restricted model minus sum of squares due to errors from the unrestricted model divided by number of restrictions by sum of squares error from the unrestricted model by df of SSE from the unrestricted model. I hope you remember this. Okay, so now I have already provided to you the beta hat from the unrestricted model, like when we would have the full model. In that case, the beta hat values were like this. Okay, we had beta hat unrestricted as minus 36.604. I'm just writing down the values because I have already kept it calculated. 396. This is minus 0.113. Okay, so sum of squares error from the unrestricted model, the formula is y transpose y minus beta hat x transpose y. Okay, this is the formula for sum of squares errors. Now if we just use the y vector that we had used previously and the x model matrix that we had used previously and this beta hat, so I am writing here unrestricted. So if we plug in all the values, we would get sum of squares error something equal to 48.124. Okay. Now we have to find out the degrees of freedom of this sum of squares error from the full model. Now that would be n minus number of parameters that we are estimating in the unrestricted model. So here we have 1, 2, 3, 4. 4 unknown parameters that we have estimated. 4, 1, 2, 3, 4. So it would be 4. And here we have n equal to 8 observations. Total n is 8 here. 4 from here, 4 from here. So n minus 4, this df is 4. 8 minus 4 equal to 4. Okay, and number of restrictions, how many restrictions do we have? H naught is alpha naught equal to 0 and alpha 1 equal to 0. So we have 2 restrictions. So we have this figure, we have this figure, we have this figure, we have this figure. What is left? The thing that is left is sum of squares error from the restricted model. So then we have to compute this thing from the restricted model. So unrestricted model was y equal to beta naught plus beta 1 x plus alpha naught z plus alpha naught xz plus epsilon. The restricted model is alpha naught is set to 0, alpha 1 is also set to 0. So this is beta naught plus beta 1 x plus epsilon star. Let us denote this by x star. So y remains the same, whatever we had here, 51, 8, 68, 25, 49, 42, 50 and 14, I think. Sorry, 49, 42, 50 and 36 we had here. 50 and 36. So this was whatever we had y. Now x star would be only the intercept column and the x column. So first we had written a and then b. So similarly we are going to write this 18, 10, 22, 12. And then the rest 19, 17, 18, 16. Okay. So from this model we would get beta hat restricted as x star transpose x star inverse x star transpose y. So if we use this model and using this formulation, we would have beta hat restricted as minus 36.06 and 4.678. So then sum of squares error from the restricted model would be same formula, y transpose y minus beta restricted transpose x star transpose y. Just remember this formula, okay? This is very important. So then we would get this thing as 69.08413. So once we have the sum of squares error under the restriction, then we are free to go ahead and use the F statistic, which is SSE restricted minus SSE unrestricted divided by the number of restrictions by SSE unrestricted by df of SSE unrestricted. So here we'll just plug in the values. This will be 69.08413 minus sum of squares error from the full model was this thing 48.124. We are going to divide this by the total number of restrictions, that was 2, by 48.124 by the number of parameters estimated in the unrestricted model. So we had 4, 8 observations. So this would be 8 minus 4, 4. And the final value of the test statistic would be, if you calculate, how much are you getting this as? Can somebody calculate? Are you getting this something like this? Okay, so you would get the F observed statistic something like this. Now, what should be the rejection rule? The rejection rule is we would reject H naught if and only if F observed is greater than F this one and this one. So 2 4, 0.05. So if this is the F distribution, if this is the point above which 0.05, the area is 0.05. Okay. So from the F table, now we are going to find out this cutoff point. So here we have the F table. So we want to find out F24. Okay, and this is given for alpha 0.05. So F24 is this value 6.94. This one is 6.94. So our decision is the observed F value is less than the critical F value. So our decision is we do not reject H naught. What was the H naught all about? H naught was alpha naught equal to 0, alpha 1 equal to 0. So we are not rejecting H naught. That means the implication is that a single line can fit the entire data. Okay. So the answer is yes, H naught is H naught is accepted in some sense. Like fail to reject it should be. Just remember, accept is fail to reject. This is more appropriate. Okay, so then we see that yes, a single straight line model is enough to fit the data corresponding to two categories. Is it okay? Any doubt? Okay. So moving on. So we have two sets of data involving values of x and y, but we are unsure whether to fit the data separately or together. Let us consider fitting an 8-parameter model where z is a dummy variable whose value is 0 for set A and 1 for set B. What hypothesis would you test to answer the question, will a single straight line fit all the data? So for category A, all z's would be 0. So our model will be alpha naught plus alpha 1x plus alpha 2x square plus alpha 3x cube. For category B, y would be alpha naught plus beta naught plus alpha naught plus beta 1x plus alpha 2 plus beta 2x square plus alpha 3 plus beta 3 x cube. So what do you think should be the answer? Anybody? Okay. So we have to fit a straight line. So line would be y equal to mx plus c. We should be careful not to fit anything with quadratic or x cube terms. Okay. single straight line. So first is to take care of this straight line thing. So in order to fit a straight line, alpha 2, alpha 3, beta 2, beta 3 should be 0. Okay. So then both for category A and category B, we would not have any quadratic or cubic terms. Now, in order to have a single line, the difference is here, alpha naught plus alpha 1x. Here we would have alpha naught plus beta naught and alpha 1 plus beta 1x. If so, here beta naught and beta 1s are extra. So if we also set those also to equal to 0, then we would just have one straight line. Okay, straight line meaning it's not quadratic or cubic, it's like y equals to mx plus c. The power of x is 1. So the correct answer is option C. Is it clear? Okay. So the next question is, the distribution of the test statistic to test hypothesis in problem 5 is what? So the distribution, we know it should be it's a joint hypothesis. So the test statistic, what should it be? Should it be an F statistic or should it be a T statistic? Can you unmute and say? So since this is a joint statistic, it should be an F statistic. Is it clear? And any questions why it should be an F statistic? Alright. So time and again we have spoken about this. If we have multiple joint hypotheses, we should go for an F test. So the test statistic is an F distribution. Now, what are the DF1 and DF2? So the test statistic is what? Again, we'll consider that unrestricted versus restricted framework. So this is sum of squares error from the restricted model minus sum of squares error from the unrestricted model divided by the number of restrictions by sum of squares errors from the unrestricted model by df of sum of squares error from the unrestricted model. So this would follow under H naught if R, number of restrictions, would be the df1 and df2 would be the df of sum of squares error from the unrestricted model. Now the actual model was this thing. The unrestricted model was y equal to this one. I'll write it here properly. Y equal to alpha naught plus alpha 1x plus alpha 2x square plus alpha 3x cube plus z beta naught, or I wrote it with respect to category, so I'll write it like this. Okay. Beta naught plus beta 1x plus beta 1x square plus beta 3x cube. Okay, so we had 1 2 3 4 5 6 7 8 8 parameters to estimate from the unrestricted model. So then the DF of SSE unrestricted would be n minus 8. And the number of restrictions, how many did we have? So we had 1, 2, 3, 4, 5, 6 restrictions. So then R would be here 6. So this is the distribution of the test statistic. Is it clear? Number of restrictions. How many parameters are we setting to 0? 1, 2, 3, 4, 5, 6. So 6 restrictions. And in the unrestricted model, we had 1, 2, 3, 4, 5, 6, 7, 8. 8 parameters. 8 parameters to be estimated. So n minus, that DF of error would be n minus the number of parameters estimated. So this will be the distribution of the test statistic. Is it clear? Okay. Okay. So we considered the following estimated regression model, where we are modeling wage on gender, education, experience and tenure. Okay. The data is based on 526 individuals. The R-square value is 0.364. So how would you interpret the coefficient on gender dummy? So the first thing that we should see is that the gender dummy is negative, and terms like female is only represented over here. So the reference category is male. Okay. So keeping everything else constant, so if I consider this as a dummy variable where 0 is male and 1 is female, so 1 unit increase, or compared to compared to males, females would have minus 1.81 units less wage, provided everything else remains constant. So what it actually measures is the average difference in wage between a female and male given same levels of education, experience and tenure. Because this is actually marginal effect. Marginal effect is what? Keeping everything else constant, what happens if we increase 1 unit of this regressor? How does my y change? Okay, so keeping everything else constant, it measures the average difference in wage between a female and male. Now, are females getting more or less? So since the coefficient is negative, so it implies that women and men having same education, tenure, experience, but women earn 1.81 rupees less on average than men. Is it okay? If it would have been positive, then we could have said that, on an average, females with the same education, tenure and experience earn this much amount more than men. Since this is negative, we say it's less. Is it okay?
Okay, ma'am. Ma'am, suppose in the dummy variable, if you taken a male as 1 and female as 0, so is there any different conclusion in our interpretation?
Yes, if so, whatever is the zero thing, so then we would, first thing is the numbers will change. Okay, so or to be very frank, here if we had written male, then the sign would have become positive in this case. So in that case we would interpret in terms of males. Okay, given the same data, for females we are saying they are earning less. If it would have been males, we would say that males are earning more.
Okay.
The interpretation will change in that manner. Whatever we have to note that we are comparing this category with the reference category. So accordingly the interpretations are going to change. Is it okay?
Okay.
Okay. So moving on. So we have this linear probability model. So the stochastic error term follows what? So linear probability model, y would follow either 1 with probability pi, 0 with probability 1 minus pi. Okay, since it's a linear probability value. Now if I have to write epsilon, I can write it as y minus beta 1 minus beta 2 xi. Okay, so when yi equal to 1, so with probability pi, epsilon I value will be 1 minus beta 1 minus beta 2 xi, and with probability 1 minus pi, y will be 0, and at that time epsilon would be minus beta 1 minus beta 2 xi. X is always fixed, so epsilon I is taking two values based on two probabilities. So the error term is going to follow a Bernoulli distribution. Is it okay? It is taking just two values with certain probabilities. Okay, so then that is why it is following a Bernoulli distribution. Alright, so moving on. Suppose we have the following estimates from a probit model with intercept and two explanatory variables, then what is the probability that y equal to 1 given that x1 equal to 0.4, x2 equals to 1? So a probit model is written as probability y equal to 1 given, let's say, x equals to phi of beta naught plus beta 1 x1 plus beta 2 x2. Okay, so this is the form of a probit model. In case of probit or logit model, so in general, if I have to say, probability of y equal to 1 equals to some g of plus beta 2x2 plus beta k xk. Okay, so this g is known as link function, which is going to transform whatever input you give here from minus infinity to plus infinity. This g function is going to transform that thing into zero and 1 range. Okay, so this is the link function. For probit we would have this thing, okay, function which is the cumulative probability distribution of a normal distribution, and instead of normal, if we have a cumulative probability distribution of a logistic regression, then we would have a logit model. Okay, so this g is nothing but a cumulative distribution function, or the CDF. This is the general concept. Now we move on to a probit model. So we have something like this. Now we have to find out what is the probability of y given x1 equal to 0.4 and x2 equal to 1. So we have to find out probability y equal to 1 given x1 equal to 0.4 and x2 equal to 1. So that will be phi of, so we have beta naught hat here, minus 1.6 plus beta 1 hat is 2 into x1 value is 0.4 plus 1, sorry, plus 0.5 beta 2 hat into x2 is 1. So this would be phi of minus 1.6 plus 0.8 plus 0.5. This would be phi of minus 0.3. Okay, so from the table, this one is the standard normal table, and these values like phi of minus 3.4 is 0.0003. Okay, so then phi of minus, what was it, minus 0.3 is here, 0.3821. Okay, so which is approximately 38%. Is it okay? All right. The next one. Suppose we have the probit model estimated using 2380 observations. So this is my estimated probit model. So what is the change in predicted probability when x increases from 0.3 to 0.4? So what is probability of y equal to 1 given x equal to 0.3? That is phi of minus 2.19 plus 2.97 into 0.3. This will be phi of minus 2.19 plus 0.891. That is phi of minus 1.29. Nine nine six minus 1.3, let's say 30. So this one, the value is minus 1.3. Zero point 968. Okay, 0.968. And this one, y equal to 1 given x equal to 0.4, this is phi of minus 2.19 plus 2.97 into 0.4. This will be okay. So in the solution that was released, here only they are doing the round up. Okay, so in the solution that is given, you will find this as phi of minus 1.29, and that will be from the table would be this value 0.0985. And this one, it would be 2.97 into 0.4. This is minus 2.19 plus 1.188. Okay, so we are going to do a round up over here, plus 1.19. This will be phi of minus 1, and that will be this thing 0.1587. Therefore, the increase in probability, so we are seeing from 0.09 it is increasing to 0.15. So there will be increase in predicted probability by how much percent? 0.1587 minus 0.0985, that is 0.0602, which is approximately 6.02%. Okay, so there will be an increase in probability by 6%. Is it okay? So if such problems are given, since we are calculating this normal probability distributions using uh, two decimal places, so first decimal, so from here if we have to find out phi of minus 1.47, we would go to minus 1.4 and then to the second order digit 1 2 3 4 5 6 7, and we would find out this one 0.0708. So for that reason, I think whatever calculation you do, you round it up to two decimal places and then we just add and subtract and then get the values from the table. Is it okay? But the problems will not change too much drastically, because if we consider this one as well, phi of just alternatively I'm saying phi of minus 1.3 would be 0.0968 and phi of this thing minus 1.188 minus 2.19 minus 1.002. This will be also minus 1.002. Approximately this will be from the table minus 1.0 only, and that value is 0.1587. So the difference will be 0.1587 minus 0.0968. So then this would be 0.0619, which would be 6.2%. Okay, so the answers might change like this. So it's better to consider to round up till second decimal places and then calculate the increases in probability. Okay, first you round it up and then proceed. All right, so moving on. So a generalized linear model is a generalization of the ordinary least squares linear regression that allows for response variable to have an error distribution other than the normal distribution, which is true. Okay, so we have seen that the errors will not be normally distributed because y is categorical. It follows some, it is not continuous, not normal. Okay, it could be binary, it could have a 0 1 case, it could be like count variables. Okay, 0 1 2 n, all discrete. So those discrete models will not have an error distribution that is a normal distribution. So the statement that the GLM is a generalization that allows for response to have an error other than normal is actually true. Any questions, doubts so far? Okay. So suppose you have been given a fair coin and you want to find out the odds of getting heads. Which of the following is true for such a case? So odds of getting heads equals to probability of getting heads by probability of not getting heads. So in a coin situation, this is probability of getting heads by probability of getting tails. Now it has been given that it's a fair coin. So for a fair coin, probability of heads will be half and probability of tail will also be half because it's a fair coin. So if we repeat the tosses, if we repeat tossing 500 times, 1000 times, 10,000 times, as and how we increase the number of trials, we would see that the number of heads and number of tails that we are getting are almost equal. Okay, so for a fair coin, this probabilities will always be half and half. If it is a biased coin, then the probabilities between heads and tails would differ. But since it is fair, it has heads and tail have equal chance of arising. Okay, so here we would have half by half, that is 1. So the odds of getting heads will be 1. So the correct answer is C. Probability will be 0.5, but odds will be 1. Is it okay? Because the formula for odds is the odds of that thing versus odds of not that thing. So if I have to find out the odds of a disease thing, then it would be probability of the disease, of individual getting the disease, odds of an individual getting a disease will be probability that the individual is afflicted with the disease by probability individual is not afflicted by the disease. Okay, so this is the definition of odds. Is it clear that odds is not always equal to probability?
Ma'am, here we can say that P upon 1 minus P also.
Yeah, of course. If you designate this as P, then this is P by 1 minus P.
Okay.
Where P, if you say, is the probability of getting the disease. Sorry. Okay. So let us consider this logistic regression model. So we have fit maximum likelihood estimation, and we've gotten these beta 1 naught hat and beta 1 hat and beta 2 values. Now to find out the odds of this bronchopulmonary dysplasia for an infant weighing 1 to 0 grams. So odds of BPD is probability individual gets BPD by probability individual does not get BPD. So this is pi by 1 minus pi. Okay. So then the odds, the required odds will be pi hat by 1 minus pi hat. Okay. That is estimated, which would be e to the power 4.0343 minus 0.0042. What is the weight? 1200. How much do we get this as?
e to the power minus 1.00
e to the power minus 1.0057.
0057.
This is coming out as
2.7182.
minus, it is not plus.
Minus 0.0057.
No, no, no. This
E
is
to the power.
something else. E to the power.
Uh,
So this is e to the power minus 1.0057. 0.3658. Are you getting this?
yes, I'm good.
Okay. So this is the odds of developing this BPD. So the odds of developing BPD is like 36% more given for an individual who's weighing 1200 grams. Okay. So and then the predicted probability of BPD. So what is the predicted probability? We have to find out pi hat, because that is equal to probability y equal to 1. Okay. So the predicted probability of developing this disorder is pi hat. So we know that the odds we got it as 0.3658. So then solving from here, we would have 1 minus pi hat 0.3658 minus 0.3658 pi hat. Keeping all pi, bringing pi hat to one side, we would have 1.0658 equal to 0.3658, which implies pi hat will be 0.3658 by 1 plus 0.3658. This would be how much? Zero point 2678. Are you getting this? So for an individual weighing 1200 grams, the probability that he might develop into he might get this pulmonary disorder is like 20%. Okay. The odds are also less than 0.5. So if odds are greater than 0.5, it means that the chances are higher of developing in a very crude sense. Okay. Is it clear? Can I move on to the next one? Okay. So the question is, Which of the following statements are correct concerning the logit and probit models? The first one is the logit model can result in too many observations falling exactly at 0 and 1. Is it true? This thing? No. Why? Because logit function will transform like I said, this probability 1 equal to 1 equal to gz, where z can lie between minus infinity to infinity, but gz will lie between 0 and 1. It's always a fractional value, mostly a fractional value. So it cannot result in too many observations falling exactly at 0 or 1. This would have been this would have been possible if we would have a linear probability model that we have truncated at 0 and 1, so that the regression equation is somehow constrained and it's not exceeding, it's not taking a negative probability, predicted probability, or taking a probability, predicted probability which is greater than 1. Okay, so this statement is not true. They use different model transformations so that probabilities are between 0 and 1. This is true. They use some sort of transformation such that the predicted probability is between 0 and 1. So in logit model, the marginal effect is simply given by the relevant parameter estimate, where the same is not true for probit model. This statement is false. Okay, because in logit model, in any kind of model, the marginal effect is given by the parameter effect into the cumulative, into the link function. Okay, so whatever is the link function or the CDF or cumulative probability distribution, there we have to plug in values to get the marginal effect. So this statement is not true. Okay, and this one, the probit model, is based on cumulative logistic distribution. This is also false, because probit is based on cumulative normal distribution. For probit we would have, so this is my probit thing. We would have probability y equal to 1 equal to phi of beta naught plus beta 1 x plus beta 2 x2 plus dot 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 beta k x k. If I write the entire thing as z, then we would have probability y equal to 1 equal to phi z, where this is the CDF of a normal distribution, normal 0 1 distribution. Whereas if I have a logistic model or a logit model, we would have this equal to 1 by 1 plus e to the power minus beta 1 plus beta 1 x1 plus beta k x k. Okay, if I write this as z, we would have 1 by 1 plus e to the power minus z. Okay, this is the CDF of a logistic distribution. Is it okay? All right. So suppose we have the following logit model that use the data on y, x1 and x2. Now given mean values of x1 and x2, what is the effect of a unit increase in x2 on the estimated probability? Now we have used a logit model. So the actual thing is that we would have something like log of pi hat by 1, sorry, so this would be okay. If I write the logistic model at first, then we would have log of p by 1 minus p, let's say, equal to this thing 0.1 plus 0.3 x1 minus 0.2 x2. Okay, now we have to find out the effect of 1 unit increase in x2. So then we have to, what we have to find out is the marginal effect of x2. So how do we find m2 equal to beta 2 into g of z, where g is the CDF of logistic. So if we have to write it down, then marginal effect 2 will be beta 2 into 1 by 1 plus e to the power minus the estimated equation. So we would have 0.1 plus what was the thing, 0.3 x2 plus minus 0. x1 minus 0.2 x2. Now we have been given x1 bar, the average, as 0.5 and x2 bar is 0.8. Okay, so then the marginal effect would be beta 2 hat is how much? Beta 2 hat is minus 0.2. So this will be minus 0.2 plus 1 by 1 plus e to the power minus 0.1 plus 0.3 into 0.5 minus 0.2 into 0.8. So this will be minus 0.2 plus 1 by 1 plus e to the power minus 0.1 plus 1.5 minus 1.6. Sorry, minus sorry. This will be 0.1 plus 0.15 minus 0.16. So it would be minus 0.2 plus 1 by 1 plus e to the power 0.1 minus 0.01. So we would get this as minus 0.2 plus 1 by 1 plus e to the power minus 0.09. So this would be minus 0.2 plus 1 by 1 plus e to the power minus 0.09 will be will be 0.913. Okay, so we can write this as minus 0.2 plus 1 by 1 plus 0.91 is equal to minus 0.2 plus 1 by 1.91. This will be minus 0.2. I'm really sorry, I've been writing plus from here. It will be multiplied. Sorry, would have multiplied. Into 0.5235 to minus 0.2 into 0.524 or 52 would be minus 0.104, approximately minus 0.1. So the answer is this falls by 0.1 0.1, sorry, falls by 0.1. Is it okay? So had it been in case of a probit model, instead of writing this thing, we would have written phi. And whatever in between we would have gotten phi of that thing, we would have taken it from the normal distribution table, and then we would have got this thing. Is it okay?
Okay, ma'am.
Okay, so this was all that I had for today's session. Do you have any questions from today's session?
Ma'am,
Hmm.
ma'am, sometimes we cannot understand. The question is given, okay, in a binary operation is the given, but we don't understand where we should use a logic and a probit model. In which situation is there? Where should we use these two?
So both are transformations. If you have to do something very because this probit model is very widely used and normal distribution doesn't have this complex formula, so uh, you could use either of the two.
Okay.
Uh, so the thing is, if you believe that your errors, okay, specifically the errors, they can or might as well follow a normal distribution, they might have a bell shaped curve. So in those cases it is wise to go for a probit modeling. But if you feel that the errors are also not normally distributed, then those kind of things would be it would be wiser to use a logic equation. Mostly what happens is that if you have binary cases, no, yes, no, or classification problems, like you have to put something to some category, most commonly the logistic regression is used. Okay.
Okay, ma'am.
Um, there are few articles also online which will show you like what are the advantages of using a probit model over a logistic model. But that since this logistic function has a very like it's related to that odds ratio or the log odds of something happening versus not happening, so modeling those kind of situations, it is the logistic model is more commonly used.
Okay.
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 That's it. And also there are some articles which say that these are more robust, the logistic ones. So mostly, very commonly, you will find this logit model instead of the probit model. That is less commonly used. But both can handle the same sort of uh, things like binary or categorical responses. Okay, anything else?
Okay, ma'am. Then we can say that if we are using a Pobit model,
Hmm.
then we have to consider that the error are to be believed to follow the normal distribution.
Yes.
Okay. Thank you.
Okay. Any other question? I would want you to be very careful about interpreting the uh, coefficients that come out of a logit and a probit model. Okay, because these are not as straightforward as it was in a linear case. So whatever we have, let's say if we have a logistic regression, then instead of that beta parameter, if we that e to the power beta will have a separate interpretation in terms of the odds or the odds ratios. Okay, so try to work that out, and if you have any problem in interpretation, please let me know in the next class, then I'll make a designated slide for the interpretation purpose, because whatever you give, the softwares are going to throw the likelihoods and the odds ratios and the coefficients only, but the interpretation will differ accordingly. Okay, so
Okay, ma'am.
just be very careful and try to interpret it. I'll see if in the practical session, if there's something, if I can show an example, I'll try to do that.
Okay.
Okay, so if
Ma'am, one more.
yes, yes.
Ma'am, like if I using an odd ratio,
Hmm.
I suppose it comes to be like 0 plus 0.9.
Hmm.
Then we can interpretation something different. Okay, like 1.9 times of uh,
Is
this
greater
much.
than one, odds ratio we have to compare with respect to 1.
Okay, okay,
Okay, if it is greater than 1, then it is increasing.
okay, okay. And at the same thing, it's the same thing if we are considering when you find the coefficient, the
Hmm.
interpretation will be the different.
Yes.
Same model.
Yes,
Okay.
yes. So the coefficient, the interpretation is going to change. So if we have something like, so if you have this log thing, hmm, so we have this model, right? Equals to alpha naught plus beta naught x something. So e to the power beta naught would give the log odds ratio, or sorry, the odds ratio when x equals to this thing. Okay, so I'm not able to show it right away, but Hmm. So beta 1, if I have, so this beta naught is exactly the change, sorry, yes. So can you see it's not coming? So whatever this beta naught is, beta naught is log of p by 1 minus p when x equal to x, sorry, 1 second. So in case of anything, we are in, let x have some base value x naught, okay. So we have log of p by 1 minus p equal to alpha naught plus beta naught x naught. Now if x is changed by 1 unit, let's say everything else is constant, then we would have something log by 1 minus p star equal to alpha naught plus beta naught x naught. So if we do 2 minus 1, then we would have log of p by p star by 1 minus p divided by p by 1 minus p equals to beta naught. So this one, this is the odds of y equal to 1 when x equal to x naught plus 1, and this is the odds of y equal to 1 given x equal to x naught. So what exactly beta naught is signifying, it is the log odds ratio that we are getting when we are changing x by 1 unit. So interpretation, this is not the marginal effect, this is exactly the log of odds ratio. So if I have to find out the odds ratio for unit change in x, then the answer will be e to the power beta naught. Is it clear?
Okay.
So these, in this manner the interpretations are going to change. This p by 1 minus p is actually odds, but this one is the ratio of two odds, so this is the odds ratio. Is it okay?
Okay.
Okay. Any confusion? Do you want me to explain once more?
No, ma'am. It's okay.
Okay, okay. Okay, then that's all for today. Thank you so much for joining. I'll see you next
Thank,
time.
thank you.
Thank you.